In this video, I'm going to introduce the concept of center of mass. I'm going to show you how to calculate the center of mass of a system of masses, and I'm going to show you how Newton's laws of motion work for a system of masses and how we can use center of mass to understand Newton's laws of motion for a system of masses, and show you how we can use the concept of center of mass to solve some problems that would otherwise be tricky to solve. Let's say we have two equal masses. Say they're both 5 kilograms and they're separated by a distance of 2 meters. So if we want to figure out where the center of this system is, where's the point that's right in the center of this system of masses? Well, it's pretty clear here that it's going to be halfway between the masses. So for this system, it makes sense that our center of mass position, x center of mass, should be halfway in between. It should be 1 meter away from that left mass and 1 meter away from that right mass. So that x center of mass is right halfway in between. Okay, but what if instead we had a 5 kilogram mass and we had a 10 kilogram mass? And these are separated by a distance of 2 meters. Well, we could define a center position, the centroid of this system, that would be right halfway in between. But from sort of an intuitive point of view, it makes sense that the real center of mass of this system should be closer to this 10 kilogram mass. There should be some point that we can define which is over here, a little closer to the 10 kilogram mass. So what we can do is just take a weighted average of the positions of these two masses, and we call this weighted average the position of the center of mass. So we define this position of the center of mass. We call it x center of mass, and we define it with this equation. We say big M, which is the mass of the whole system, times the position of the center of mass, equals the sum over I of the MIXI. We take each mass, MI, M1, M2, M3, and so on, and we multiply it by its position, XI. So this sum, when we evaluate it, it looks like M1 times X1 plus M2 times X2 plus M3 times X3, and so on. Remember, this big M here is just the total mass of the system, so it's just the sum over I of all the MI. This is M1 plus M2 plus M3, and so on. So this gives us a position of the center of mass, which is 1 over the whole mass of the system times the sum of all the MIXI. So let's evaluate the position of the center of mass for this system of two masses, a 5 kilogram and a 10 kilogram. Well, first I have to define my coordinate system. I'm going to call this here x1 equals 0, and I'm going to call this over here x2 equals 2 meters. So I've defined my coordinates. I have an x-axis that starts here at 0 and goes off in that direction. Okay. So now my position of the center of mass formula is x center of mass equals 1 over big M times the sum over I of MIXI. Well, this equals 1 over big M is 5 kilograms plus 10 kilograms. And then I multiply this by the sum of the MIXI. So that's M1, which is 5 kilograms, times X1, which is 0, plus M2, 10 kilograms, times X2, which is 2 meters. So when I add all this up, I get this is 20 kilogram meters over 15 kilogram meters. The kilograms, it's not kilogram meters, it's just kilograms in the denominator. The kilograms cancel out, and I get 20 over 15, which is 4/3 of a meter. That's 1 1/3 meters away from the origin of this coordinate system. So this center of mass position right here is 1 1/3 meters away from the left-hand mass. You can see it's a little bit more than halfway between the two masses. It's a little closer to this 10 kilogram mass. The fact that this 10 kilogram mass has more mass pulls the center of mass towards the 10 kilogram mass. It pulls it a little bit closer to 10 kilograms than it is to 5 kilograms. So that's the basic idea of the center of mass of a system of masses. And I can do this for 2 masses, but I can do it for 3 masses, 4 masses, 5 masses, as many masses as I want. I just add up all the MIXI and divide by the total mass M of the system. So for the system of 2 masses, we get this equation: x center of mass equals m1 x1 plus m2 x2 over m1 plus m2, which is 1 1/3 meters. Now, we can also define a velocity for the center of mass. So let's just say in this case, this mass here is going to the left with a velocity v1 equals 1 meter per second. And this mass here is going to the right with a velocity v2 equals 1 meter per second. And the way I'm defining my coordinates here, I should make this velocity here negative, since it points in the negative x direction. So let me just do that. This should really be negative 1 meter per second. Okay. So if I want to calculate the velocity of the center of mass of this system, well, the center of mass, the velocity of the center of mass is just the rate of change of the position of the center of mass. This is just the derivative with respect to time of x center of mass. This is d by dt of m1 x1 plus m2 x2 over m1 plus m2. My masses are all constants here, so this derivative just ignores those constant masses, and it looks like this: m1 dx1 dt plus m2 dx2 dt, all of this over m1 plus m2. Well, dx1 dt and dx2 dt, those are just v1 and v2. So this v center of mass is going to equal m1 v1 plus m2 v2 over m1 plus m2. Okay, so you can see just by taking the derivative with respect to time of x center of mass, I get v center of mass, which looks like almost the same formula, but instead of being a weighted average of the positions, it's a weighted average of the velocities. Well, this here equals, for this particular case, this is 5 kilograms times negative 1 meter per second plus 10 kilograms times 1 meter per second. All of this over 5 plus 10 is 15 kilograms. If I plug this all into my calculator, I get 1/3 of a meter per second. So this position of the center of mass is moving in the positive direction. V center of mass equals 1/3 of a meter per second. Because this 10 kilogram mass, they're both moving with the same velocity in opposite directions. So if they had the same mass, the speed of the center of mass would be 0. But because this 10 kilogram mass is bigger, the velocity of the center of mass goes to the right. It's more weighted towards this positive velocity than it is towards this negative velocity. Okay, so this is the concept of velocity of the center of mass. Really simple. We just take the derivative of the position of the center of mass with respect to t. And as I'll show you in a minute, if there are no external forces, then the velocity of the center of mass is conserved. So if I don't have anything outside of this system of masses pushing on it, the velocity is going to remain constant. It's not going to change. So velocity of the center of mass is a conserved quantity for a system with no external forces. If I have external forces, then the position of the center of mass of the system is going to accelerate and the velocity will change. That's what I'll show you next. What I just showed you was the position and velocity of the center of mass for a system of particles in one dimension, that is, where all of the masses are along a straight line. If that's not the case, if my masses aren't all along a straight line, I can still define the position of the center of mass, and the formula looks very much the same. my position of the center of mass, now instead of being an x, it is an r center of mass, and it equals 1 over m times the sum over I of all the mi ri. Okay, so this is like, what this really is a position in all three coordinate directions. I have an x center of mass, which is the same formula I showed you before, 1 over m sum over I mi xi. I have a y center of mass, it's 1 over m sum over I of mi yi. And I also, in 3 dimensions, I'll have a z center of mass, 1 over m sum over I of the mi zi. Okay, so for a collection of masses in 3 dimensions, I can just generalize this concept of position of center of mass to a 3-dimensional position of the center of mass. Okay, so let's say we have a system of 3 masses in 2 dimensions like this. Just m1, m2, and m3. So there's some position of the center of mass we can calculate with our formula. And let's just say that these 3 masses exert some forces on each other. So m1 and m3 exerts a force F31 on m1, m1 exerts F13 on m3, m2 and m1 exert forces on each other, F21 and F12, and m3 and m2 exert forces F23 and F32. These are attractive forces. These might be tied together with strings. They might be tied together. They might have springs between them. They might have a gravitational attraction. It doesn't really matter why these forces are here. We just know they are here. Okay, so we know that the position of the center of mass, R center of mass, equals 1 over the total mass of the system times m1 r1 plus m2 r2 plus m3 r3. We can find the velocity of the center of mass of the system. This is 1 over m. Well, we just take the derivative of our center of mass. So m1 dr1 dt is v1 plus m2 dr2 dt is v2 plus m3 v3. Okay. And we can find an acceleration of the center of mass. This is just going to be derivative with respect to time of velocity of the center of mass, which I can take that derivative inside. It just applies to the v's, and this becomes 1 over m times m1 a1 plus m2 a2 plus m3 a3. Okay. So now let's think a little bit about Newton's second law of motion. Newton's second law of motion says m1a1, this equals F net 1, the net force acting on mass 1. m2a2 is F net 2, net force acting on m2. m3a3 is F net 3. Okay. So this is just equal to 1 over the mass of the system times F net 1, which is for m1, F net 1 is going to be, well, it's the sum of the 2 forces acting on m1. So it is F31 plus F21. F net 2 is going to be plus F12 plus F32, and F net 3 is going to be plus F23 plus F13. Okay, so I've written out what this net force is in completely. Well, now let's think a little bit about this. Newton's third law of motion tells us that F13 equals negative F31. So that means F31 plus F13 have to add up to 0. These just cancel out. Similarly, F21 equals minus F12. So these cancel out and add up to 0. And these cancel out and add up to 0. So even though the net force on each individual mass here is non-zero, and therefore the acceleration of each individual mass is non-zero, when I sum up all these forces to get the acceleration of the center of mass, I find that all of these forces between the masses just cancel out. They don't contribute to this acceleration. Okay, so if there are no, all these forces are internal forces. They act between the masses in the system, but they're not coming from the outside. So if there are no external forces acting on the system, then I have no acceleration. And if I have no acceleration, so if A center of mass equals 0, that means that V center of mass is constant, right? Which is what I said in the previous slide. If there are no external forces, then V center of mass is constant. Well, now let's say I go ahead and add in a couple of external forces. Let's say I add in an F2 external like that, and an F3 external like that, and I'll put in a little F1 external too. So now I'm putting in an external force acting on each of these masses. Well, now Fnet1, I have to add in F1 external. Fnet2, I add in F2 external. And Fnet3, I add in F3 external. So now my acceleration of the center of mass does not equal 0 anymore. This A center of mass equals 1 over m times F1 external plus F2 external plus F3 external. Okay. So this leads me to Newton's second law for a system of masses. I can say F net equals the total mass of the system just by multiplying both sides here by this mass m. I can take this mass m, cross it off of this side, and multiply it over there. So F net equals m times A center of mass for a whole system of particles, where this F net, when I add up all the forces, I find I only get the external forces. Only the external forces matter. Okay, so this is actually a really fundamentally important result for understanding why Newton's laws of motion work in the first place. Let's think about some solid object. And let's say I apply a force F to this object. So I apply some force F. Well, in this class so far, I've said you can always just treat forces as if they're acting on the center of the object. This is really the center of mass. But when I apply this force, maybe I don't actually push on the center of the object. I push over here. So I apply a force F right over here, just on this little piece of the object here. Well, now this piece of the object exerts forces. Maybe this is an atom. I'm just pressing on one little atom over here. It exerts forces on the atoms around it, so it pushes on these like that, and these push back, and then these atoms here push back like that. These atoms here exert forces on the atoms next to them. So this atom here maybe pushes on that, and this pushes back like that, and this atom here pushes like that, and this pushes back like that, and there's this whole web, this whole complicated web of forces throughout this macroscopic object that I'm applying a force F to. And, you know, for any real object, there's going to be Avogadro's number of little atoms, and they're all exerting forces on each other. That's way too much to deal with. We can't write down Avogadro's number of copies of Newton's second law. But what this result shows us, that we can just say the total F external equals m a center of mass, means we can apply Newton's second law to the center of mass of this system. That is, we cannot worry about all of these little internal forces, and we can just say this force F acts right on the center of mass of the system like that. Oops, let me change my color. This force F acts right on the center of mass of the system like this. This is my external force. And it acts right on the center of mass. So this F external is going to cause an acceleration of the center of mass of the system, and I can just ignore all this junk over here, all these internal forces. So this is actually what we've been doing for the whole class. Every time we apply a force to a block or to a ball or to a wall or anything like that, really implicit in that has been the assumption that we can just worry about the external forces and the motion of the center of mass of the system and not have to worry about the internal forces. Now we've proven why that's true by defining this concept of center of mass and going through these equations, but it wasn't obvious that this was true when we were doing it. But I just told you, go ahead and do it anyway. Now you understand why. I'm going to do a couple of examples. First, I'm just going to show you a simple example of how to calculate the position of the center of mass for a collection of point masses. So the first thing I need to do is define a coordinate system. And I'm going to go ahead and call this the origin of my coordinate system. This will be the x-axis like that. So that direction is x. This will be the y-axis like that. That direction is y. So what I'm going to do is find the x position of the center of mass and the y position of the center of mass. Remember, there's a quantity r center of mass, which equals m times the sum over, oops, wrong. It equals 1 over m, the total mass of the system, times the sum over I of the little mi x, oops, little mi ri. But this r center of mass just really equals an x center of mass I hat. That's the x component of the center of mass position. Let's say y center of mass j hat. So I can find this x center of mass. This is 1 over m times the sum over I of mi xi. Well, m is the total mass of the system. So this is 1 over, just write this, over 2 kilograms plus 4 kilograms plus 3 kilograms plus 1 kilogram. I add up all the masses. And in the numerator here, well, I multiply each mass by its x coordinate. So this square has a side length of 1 meter. So if this is x equals 0 over here this is x equals 1 meter. So this is equal to 0 times 3 kilograms plus 0 times 2 kilograms plus 1 meter times 1 kilogram plus 1 meter times 4 kilograms. So this position of the center of mass equals, well, these zeros, just make those 0, so I get 1 kilogram meter plus 4 kilogram meters over 2 plus 4 plus 3 plus 1, that is 10 kilograms. Well, this is just 1/2 of a meter. So the x coordinate of the center of mass is just right here in the middle. This is my x center of mass. Okay, great. Now let's do the same thing for y. Y center of mass is going to equal, well, this here is y equals 0, and this here, that line is y equals 1 meter. So y center of mass is going to equal 3 kilograms times 0 plus 1 kilogram times 0 plus 2 kilograms times 1 meter plus 4 kilograms times 1 meter. And all of this will be over the total mass of the system, which I already said is 10 kilograms. This ends up giving me 6 kilogram meters over 10 kilograms. which is 6/10, that is 3/5. 3/5 of a meter. Kilograms cancel. So my y center of mass is not halfway in between, it's a little bit higher. My y center of mass is 3/5 of the way up, which is something like that. So at the end, my r center of mass is the intersection of this x and y line. This vector here is my r center of mass. R center of mass equals 0.5 meters I hat plus 0.6 meters, that's the same thing as 3/5 j hat. Okay, pretty simple. That's how you find the position of the center of mass for a system of particles in 2 dimensions. So you may be wondering, why are we worrying about all the center of mass stuff in the first place? I showed you that it's important for really understanding how to apply Newton's laws of motion, but I haven't showed you a unique type of problem you can solve just using this concept of center of mass. Well, here's one. Okay, a chihuahua walks from one end of a skateboard to the other. The skateboard has a mass of 2 kilograms and a length of 75 meters, and the chihuahua has a mass of 3 kilograms. If the skateboard can roll without friction, how far does the skateboard move? All right, so here's my chihuahua on a skateboard. This chihuahua has a mass m1. The skateboard has a mass m2. And I'm going to define a coordinate system here. Just going to use an x-axis here. I'm going to say this is the x direction. So this chihuahua has an x initial, which is 0 meters. And the skateboard has, well, the skateboard has a length L. So I'll call this length L. The position of the center of mass of the skateboard is x initial, say x initial skateboard equals L over 2. So that's half of 75 centimeters, which is what? 37.5 centimeters. Okay, so that's x initial skateboard, and this is x. Actually, let's, to make this all consistent, let's call this x initial 2, and this will be x initial 1. So chihuahua is m1, skateboard is m2. Okay, so as this chihuahua walks across the skateboard from one side to the other, the chihuahua starts out over here and walks to the right. Well, the chihuahua is going to exert a force on the skateboard. The skateboard is going to exert a force back on the chihuahua. But if there's no friction between the skateboard and the ground, the external forces acting on the system are 0. There are no external forces acting on the system. That means the acceleration of the center of mass of the system is 0. Well, this means the velocity of the center of mass of the system is constant. And if the chihuahua and the skateboard are starting out at rest, that means this is constantly 0. So the velocity is 0 the whole time. If the velocity of the center of mass is 0, that means the position of the center of mass is constant. It doesn't change. So let's calculate the initial and final positions of the center of mass. We know they have to be equal to each other. So we know that x center of mass initial is going to equal, let's write it this way actually. The total mass of the system times the position of the center of mass initial is going to be m1 x1 initial plus m2 x2 initial. We know what those initial positions are. We know that the m times x center of mass final, m times x center of mass final is going to equal m1 x1 final plus m2 x2 final. So the idea here is this chihuahua moves across the skateboard to the right. It's pushing to the left on the skateboard. So the skateboard is going to move to the left. And we want to figure out how far the skateboard moves to the left. Well, we know that this position of the center of mass is constant. So we know that x center of mass initial equals x center of mass final. This tells us that m1 x1 initial plus m2 x2 initial equals m1 x1 final plus m2 x2 final. I'm going to reorganize this equation to look like this. m1 x1 final minus m1 x1 initial plus m2 x2 final minus m2 x2 initial equals 0. Well, in here I can factor an m1 out of these first two terms. So this becomes just m1 times x1 final minus x1 initial. And I can factor an m2 out of these two terms. So this becomes just m2 times x2 final minus x2 initial. Well, this is just m1 delta x1 plus m2 delta x2 equals 0. So this tells me I multiply m1 times the displacement of the Chihuahua, so the mass of the Chihuahua times the displacement of the Chihuahua, plus the mass of the skateboard times the displacement of the skateboard equals 0. Okay, so now things get interesting. This skateboard is going to roll through some displacement delta x2 to the left, while this Chihuahua goes through some displacement delta x1 to the right. Now this delta x1 is really going to be, the Chihuahua is going from one end of the skateboard to the other, so it ends up over here at the other side of the skateboard. But the skateboard moves back to the left. So delta x1 is going to be the length of the skateboard. The Chihuahua moves the whole length of the skateboard, but then the skateboard moves backwards delta x2. So this is going to be the length of the skateboard plus delta x2. Since delta x2 is going to be negative, delta x1 is going to be smaller than L. So I get now that delta x1 equals L plus delta x2. The Chihuahua moves the distance L with respect to the skateboard, but the skateboard moves the distance delta x2 with respect to the ground. So now I have these two equations, this one here and this one here, and I have two unknowns. I don't know delta x1 and I don't know delta x2. I can solve the system of equations for my unknowns. Now what I want to find here is how far the skateboard moves. That is, I want to find delta x2. So what I'm going to do is just take this delta x1 here and plug it in up there. So I get m1 times delta x1 is L plus delta x2 plus m2 delta x2 equals 0. Okay, so now I can go ahead and solve for delta x2. I can write this as m1 delta x2 plus m2 delta x2 equals, and I'm going to pull that L times m1 over here, so minus L times m1. I can factor my delta x2 out and divide both sides by m1 plus m2. I get delta x2 equals minus L m1 over m1 plus m2. So I'm going to plug in my numbers. L is 75 centimeters, that's 0.75 meters. M1 is the mass of the Chihuahua, that's 2 kilograms. Divide that by 2 plus 3 is 5 kilograms, that's the total mass of the Chihuahua plus skateboard. And I get 0.75 times 2 is 1.5 kilogram meters divided by 5, 0.3 kilogram meters divided by kilograms, so 0.3 meters. But there's a minus sign up here. I forgot about my minus sign. It's minus 0.3 meters. So as the Chihuahua walks from one end of the skateboard to the other, the skateboard is going to roll 30 centimeters to the left. And this would be really hard to figure out just using Newton's laws of motion and kinematics. But it's really easy to figure out using this concept that the velocity of the center of mass is 0, so the position of the center of mass is constant. Okay, so you have a couple problems on your homework that look kind of like this. Maybe are slightly more complicated, but the idea is the same. If there are no external forces acting on a system, you can say that the position of the center of mass is constant, and this can let you solve problems that would otherwise be tough to solve.